We are going to focus now on aqueous equilibria. These are equilibria involving reactions in aqueous solutions because there's a lot of important reactions happening in aqueous solutions. So objectives for this lesson, you'll be able to describe equilibria involving reactions in aqueous solutions. In particular, acid-base reactions, reactions involving dissolution, and complex ion formation. Okay, I need to be able to define and calculate pH, classify solutions as either acidic, basic, or neutral, define acid and base using the Arrhenius definition, the Bronsted-Lowry definition, and the Lewis definitions. So there are different levels of definitions for acids and bases. And you need to be able to determine equilibrium constant and apply that to determining extent of reactions in aqueous solutions. All right. So the reactions we're going to be focusing on are these reactions, okay? And the KEQ for these reactions have special names that you need to be familiar with. So the reaction known as the autoionization of water or the autoprotolysis of water, also known as autoprotolysis. The KEQ for that, the equilibrium constant, is called KW. For a reaction that involves the ionization of an acid in water, the equilibrium constant is known as the K sub A of the acid, or Ka of the acid. If you're dealing with a reaction that involves ionization of a base in water, the KEQ for that is called the K sub B, or Kb of the base. And that should be easy to remember. A for acid, B for base, W for water. If you're dealing with the dissolution of an ionic compound in water, okay, the equilibrium constant for that is known as the KSP. SP stands for solubility product. As you'll see, the expression for that, KEQ, it's just going to have a product. The denominator is going to be 1 since the activity of a solid is equal to 1. That's why it's called solubility product. And finally, for the formation of a complex ion, this is formed by a metal cation and ligands. These are ions or molecules that are capable of what we call coordinate covalent bonding. They have lone pairs to share with the metal. Okay. The equilibrium constant for that type of reaction is known as the K sub F, or the formation constant of complex ion. So let's start with the autoionization of water. Okay. Like I said, KQ for the reaction, for this reaction, is known as KW, and this particular reaction is this one right here. Okay. In water, okay, even if you have pure, ultra pure water, it's not all going to be just water molecules. So at any given instant in ultra pure water, a very, very tiny fraction of your water molecules are actually in the form of hydronium and hydroxide ion. And the way these are formed, okay, let's say you have two water molecules, is a proton can hop from one molecule to another. In fact, protons do that a lot in water. They hop from one molecule or ion to another. So as long as they find a lone pair that they can latch onto, they can hop to it. Okay, so when this happens, when a proton, H plus, transfers from water to another water molecule, you get hydroxides left behind, right? This is going to be your hydroxide that's left behind, and you make hydronium ion. So H plus H2O will give you hydronium ion. So this reaction right here occurs to a very small extent, but it does occur. It's significant, and it's significant enough to make a big impact in a lot of systems, especially living systems. So this is what's known as the autoionization. It's autoionization because it just happens in water automatically, in a way. And you can abbreviate this by just writing it as H2O liquid yields H plus aqueous plus hydroxide. So when we say H plus aqueous, what we really mean is hydronium ions. Okay, none of those H pluses are actually by themselves. They're latched onto another water molecule. Some of them may be latched onto two water molecules. Okay, so it might be surrounded by several water molecules. So we're just going to abbreviate that as H plus. Okay, so Kw is H3O plus times OH concentration of hydronium ion, or more precisely, the activity of hydronium times the activity of hydroxide. Or we can write that as activity of H plus times the activity of hydroxide. Now, this is a value you have to memorize. At 25 degrees Celsius, the value of Kw is 1.00 times 10 to the negative 14. So if you have pure water, what do you think H plus and hydroxide is going to be at 25 degrees? Let's look at this reaction again. Oops. Let me write that as H plus plus hydroxide, and Kw is 1.00 times 10 to the negative 14. 10 to the negative 14, is that a very big number or a very small number? Very small number. So you can say you're going to have just trace amounts of hydrogen and hydroxide ions in water, in pure water, right? And if you're going to lose X moles of water, then you get, if you make X moles of H plus, then you're also going to make X moles of hydroxide. So in pure water, you're always going to have equal amounts of hydrogen ions and hydroxide ions. So how would we solve for X here? So H plus and hydroxide would be the same, right? And so let's just say it's equal to X. What's the expression for Kw? Equilibrium constant is activities of products over activities of reactants. So it's going to be H plus times hydroxide divided by activity of water is 1, right? So that's just going to be X squared over 1. So how do we solve for X? 1.00 times 10 to the negative 14 equals X squared. So that means X must be equal to 1.00 times 10 to the negative 7. So that is the concentration of H plus and hydroxide in pure water. Okay, so H plus times hydroxide. Okay, this would be 1. H plus and hydroxide will both be 1 times 10 to the negative 7. Now, if you were to add things to water, contaminate your water, the solids that you add could alter the H plus and the hydroxide concentration. You could be adding something that would give you more, that would produce H plus in water. You call that an acid. You can add something that would produce hydroxide in water. You can call that a base, right? But the product of H plus times hydroxide must be a constant. That's equal to Kw. So these two will always be equal to a constant. What does that mean? If H plus times hydroxide is a constant, okay, it's equal to a constant. If H plus goes up, what must happen to hydroxide in order for the product to remain constant? Let's go down. Like if I multiply this by 2, I have to divide this by 2 in order for the product to remain the same, right? So if this was 2 times 10 to the negative 7, okay, then this is going to be 0.5 times 10 to the negative 7 in order for the answer to still be 10 to the negative 14, right? So if one goes up, the other goes down, right? That's you've seen this relationship lots of times already. Whenever the product of two things is a constant, we say they are inversely proportional. Remember Boyle's law? Pressure times volume equals constant. Pressure goes up, volume goes down. Same idea here. Okay? So anytime you alter the concentration of H plus and hydroxide, you can still figure out what the concentration of the other one is. So calculate hydroxide if H plus is 2.50 times 10 to the negative 4 moles per liter. Now, unless otherwise specified, when we talk about these reactions, always you can assume it's at room temperature of 298 Kelvin, okay, or to be more precise, 298.15 Kelvin, since we're dealing with 25 degrees Celsius, okay? All right, so if this is the case, what's my hydroxide? How do I calculate hydroxide? I know H plus times hydroxide equals 1.00 times 10 to the negative 14. How do I solve for hydroxide? Divide both sides by H plus, right? So hydroxide is equal to 1.00 times 10 to the negative 14 divided by 2.50 times 10 to the negative 4. This one would be 1. One point zero times 10 to the negative 14 divided by 2.5 times 10 to the negative 4. And make that scientific notation. That's 4 times 10 to the negative 11. How many sig figs? 3 sig figs. Okay? So, what's higher in concentration here? H plus or hydroxide? 10 to the negative 4 versus 10 to the negative 11. Which one's higher? More H plus in this particular solution. Okay, this is greater than 10 to the negative 7, right? And this is less than 10 to the negative 7. Okay, and so when we have a solution like that where the hydronium ion concentration or H plus concentration is greater than 10 to the negative 7, you say you have an acidic solution. So this is what you would call an acidic solution. Right? So acidic solution is one where H plus is larger than 10 to the negative 7, and necessarily hydroxide would have to be less than 10 to the negative 7. Now, if it's the other way around, if your hydroxide is larger than 10 to the negative 7, then your H plus is going to be less than 10 to the negative 7. You have what's called a basic solution. Okay? And if it so happens that H plus and hydroxide are both equal to 10 to the negative 7, it doesn't have to be pure water. They can be made to be both 10 to the negative 7. Then you have what's called a neutral solution. Okay? So, test yourself. H plus is 2.5 times 10 to the negative 4. Is this solution acidic or basic? We just talked about that, right? 2 slides earlier. 2.5 times 10 to the negative 4. That's larger than 10 to the negative 7. So that's acidic. All right. If your hydroxide is 2.5 times 10 to the negative 4, is it acidic, basic, or neutral? Okay, this would be basic. Very good. All right. The definition I just gave you about acids and bases is what's known as the Arrhenius definition. Arrhenius defined actually an acid as a substance that if you put in water, it dissociates to yield H plus. So for example, HCl, he said, okay, HCl is an acid because in water, if you put it in water, it breaks up into H plus ions and chloride ions. So what's the effect of putting HCl in water? It causes your H plus concentration to go up. Okay, same thing with sulfuric acid. What does it do in water? It can give you H plus plus HSO4 negative. Okay, so your sulfuric acid is also an acid according to the Arrhenius definition. That's a substance that yields H plus in water. Okay, by dissociating. What does dissociate mean? The opposite of associate is dissociate. So that means to break apart. A base, on the other hand, is a substance that yields hydroxide in water. So, for example, sodium hydroxide, it's made up of ions. So when you put it in water, those ions are dispersed. You get hydroxide ions and sodium ions. It's these hydroxide ions that makes the substance a base. Satisfy Arrhenius' definition of a base. Okay, a base is a substance according to Arrhenius, that dissociates to yield hydroxide in water. Now, the limitation of this definition is that it doesn't explain why solutions of salts, for example, salts are ionic compounds that dissociate into ions other than H plus or hydroxide. So if something dissociates in water, ionic compound, cation is not H plus, the anion is not hydroxide, we call that a salt. Okay, salt is not necessarily sodium chloride, it's any ionic compound. Salts can be acidic or basic. For example, ammonium chloride, this dissociates in water into ammonium and chloride ion. But if you measure the hydronium ion concentration, the H plus concentration in this solution, you'll find that it's acidic, slightly acidic. Okay, but it doesn't produce any H plus by itself. So ammonium chloride, according to Arrhenius' definition, is not an acid. It doesn't break up to form H plus. But the reason it's an acid is because this ammonium can actually react with water. It can transfer a proton to a water molecule to give you H3O plus ammonia. And this H3O plus, that's what we call H plus, right? So it's this ammonium ion that further dissociates to give you H plus. So in the sense of Arrhenius' definition, ammonium chloride is not an acid, okay? But it does produce an ion that donates a proton to a water molecule. Okay, sodium carbonate, same thing. It's basic in solution. You don't see any hydroxide there, right? Sodium carbonate will give you 2 sodiums and a carbonate ion. There's no hydroxide there, but if you measure the concentrations of H plus and hydroxide here, you'll find that the hydroxide concentration is such that it's basic. So how does this produce hydroxide? It has to do with this carbonate ion. Okay, a carbonate ion can pull a proton away from a water molecule. Okay, a proton can be taken away from a water molecule to give you bicarbonate ion plus hydroxide ion. Okay, so in this sense, it's making the solution basic, not because it broke up and gave you hydroxide in water, but because one of the fragments that came from it reacted with water to give you hydroxide. Okay? So aluminum chloride is another example. Okay? Aluminum chloride gives you aluminum ions and chloride ions. Where's the H plus there? No H plus there. So, but if you put aluminum chloride in water, you're going to get an acidic solution. And the reason for that is aluminum ions in water actually surrounded by water molecules. Actually, they form what's known as coordinate covalent bonds. Okay, so this pair of electrons on the water molecule actually is bonded to aluminum, and there's 6 of these water molecules that could bond to aluminum. Okay, and that one. So and 4 more. So aluminum, when we say aluminum ion in aqueous solution, what we really mean is aluminum that is surrounded by 6 water molecules. This is actually what this means. Okay, it's actually what we call a complex ion. This is actually a covalent bond between the oxygen of the water and the aluminum. And what happens in the case of aluminum is this: aluminum ion. Remember, your OH bond is a very polar bond, right? This is already polar as it is, right? You have partial positive, partial negative charge here, right? But what does the aluminum do? It's positively charged. It's pulling electrons even further away from this H plus. This makes this OH bond even more polar. So if that OH bond is very polar, okay, this H plus can easily, okay, that's to make this H plus more readily removable, okay, so to speak. So it makes it easily more ionizable, we say. So that H plus can readily transfer to another water molecule, okay. And so what's left behind? You have your aluminum, Okay, there's got 5 more attached to it, right? 4 more water molecules attached to it. And then you have your OH. Okay, one of the H is gone, so this will now have a charge of +2 overall instead of +3, and that gives you H3O+. Okay, so this is, again, what makes aluminum chloride, this solution, acidic. Okay, in other words, the net result is you have a reaction that leads to the formation of hydronium or hydroxide ion. And what do you notice these reactions have in common? They all involve what? Moving a proton from one molecule to another or one ion to another. So we can make a more generalized definition of an acid and base then in terms of this transferring of protons, because that's what leads to acidic and basic solution, to transfer of protons. So Bronsted and Lowry came up with a more general definition of acids and bases. What they did was they classified the species, the ions or the molecules, instead of just the substance. Okay, the substance is just a collection of ions and molecules, or ions or molecules. But in the Bronsted-Lowry definition, what we call the acid and the base are the molecules themselves or the ions themselves. Okay? So according to the Bronsted-Lowry definition, an acid-base reaction is one that involves a transfer of a proton, transfer of H+, from one species to another. So any reaction that involves proton transfer is called an acid-base reaction. So this is a more generic definition of acids and bases. And so during a proton transfer reaction, the species that loses the proton, that's called your proton donor, that's your acid. Okay? So the acid is the proton donor. The species that accepts the proton, that gains a proton, or the proton acceptor, is your base. Okay? So this allows you to explain acidic and basic salt solutions as we showed earlier. Essentially, how does this explain it? The ions may react with water to form H+ or hydroxide. What did we say happened, for example, to an ammonium salt? One of these hydrogens can transfer. Okay, one of these protons can transfer as a proton. One of these hydrogens can transfer as a proton to a water molecule, giving you hydronium ion. And what did we say happened to a carbonate ion? A proton from a water molecule can hop onto this carbonate ion, leaving behind a hydroxide. Okay, so that's the Bronsted-Lowry definition. All right, so here's a quick check. For this reaction, the autoionization of water, this involves proton transfer, right? From one water molecule to another water molecule. So for the forward reaction, what's the acid and what's the base? According to the Bronsted-Lowry definition. In a Bronsted-Lowry definition, an acid-base reaction is a proton transfer reaction. The proton donor is the acid, the proton acceptor is the base. So in this particular reaction, going forward, what's the acid and what's the base? So what happened here? Okay. Let's see, what happened here? A proton transfers from here to here, right? So what's the acid? The acid is where the proton came from. The donor, what's the donor? H2O. What's the acceptor? Also H2O. So the acid is H2O, the base is H2O. Okay? So correct answer is A. Alright? So that's what we mean by Bronsted. So in this particular case, we say that the acid and the base is the same molecule, right? The same type of molecule. Water, you'll notice, is capable of donating a proton. It's capable of accepting a proton. You call it an amphiprotic species. Okay, amphi means like amphibian, can go either way, land or water. An amphitheater is what you can see it from both sides, stage, right? So amphiprotic would be a species that can either accept or donate a proton. It can either act as a Bronsted acid or a Bronsted base. For the reverse reaction, remember this reaction is reversible, in fact. So if you were going back and hydronium was to give back its proton, okay, give its proton to hydroxide to give you 2 water molecules, what's the acid for the reverse reaction and what's the base? This time, the donor is hydronium, and the acceptor is hydroxide. Okay? So, the acid is hydronium, and the base is hydroxide. Okay, so in an acid-base reaction, okay, there's when you transfer a proton from one species to another, the proton can transfer back, right? And so the reverse reaction is also a proton transfer reaction. So what did we notice? This was an acid, this was the base, right? And then what happened? This is the acid, and that's the base, right? For the reverse reaction, let me color code it. So for the reverse reaction, this is the acid, and that's the base. So where did this H3O plus come from? From a water that gained a proton, right? It came from this, right? So this H2O and H3O plus, we say, is a conjugate acid-base pair. Water is the base, its conjugate acid is H3O plus. Where did this hydroxide come from? From the water that lost the proton, right? So this thing right here, this acid and base right here, H2O and OH minus, water and hydroxide, is also a conjugate acid-base pair. So that's what conjugate acid-base means. So what's the difference between a conjugate acid and a conjugate base in the pair? The acid has 1 more proton compared to the base, right? This acid has 1 more proton compared to its conjugate base. That's the difference, okay? Let's try this one. Cyanide plus water gives you HCN plus hydroxide. The base for the forward reaction and the base for the reverse reaction. What's the base? That's the proton acceptor, right? Okay. So, what's the base? The acceptor. What happened here? This H2O lost a proton, right? It transferred over to the cyanide to give you HCN. So what's the base for the forward reaction? The cyanide. Okay, and that's the acceptor, right? What's the base for the reverse reaction? If the reaction were to go in reverse, what would have happened? How do you get back your cyanide? This H plus has to transfer over to give you water, leaving behind a cyanide. So for the reverse reaction, what's your base? It would be your hydroxide. Okay? So correct answer is A. Okay. So now let's talk about the acid ionization constant. Right? If you have a reaction where an acid, a Bronsted acid, a proton donor, donates a proton to water, for example, ammonium ion donates a proton to water, that gives you NH3, and what happens to the H? It becomes H3O+, right? Anytime you have this type of reaction, something plus water, and the something donates the proton to the water. That means the water is acting as a base, right? So that something must be acting as an acid. That reaction is called the ionization of the acid. The KEQ for that is called the Ka of the acid. So if HX is the acid, okay, what would be the reaction we're talking about here? We're talking about the transfer of H plus from the acid to water gives you H3O plus. And what's left behind? It's just going to be X minus. Okay? So this reaction right here, ammonium plus water gives you H3O plus and ammonia. Okay? And you can abbreviate this as this one. You can leave out the water and you can just write H3O plus as H plus. That would be an abbreviation for that reaction. Okay? What do you notice is the product of this reaction? And you have, anytime you have an acid donating to water, okay, you get the conjugate base of the acid. What's the conjugate base of ammonium? That's what you get when it's lost the H plus. What happens when you lost the H plus from NH4 plus? Instead of 4 hydrogens, you have 3 hydrogens, right? And you have your charge, instead of +1, will drop down to 0. So NH3 is the conjugate base. So in this particular example, you can see that your acid, ammonium, reacts with water to give you its conjugate base, which is ammonia. Water gains a proton, produces it, and you get the hydronium ion, its conjugate acid. So in the acid ionization, you have a reaction with water that leads to the formation of H3O+. Okay? So the KEQ for that, the equilibrium constant for that, is called the Ka of the acid. So what's the reaction for which the KEQ is called the Ka of HCO3-? So if it's Ka, that means it's acting as an acid. What do we say an acid is? A proton donor. So we want this to behave like an acid. So it has to donate a proton to whom? To what? Water. Okay. So anytime you have Ka of something, it's something plus water, and it's something. The something is behaving like an acid. So what happens to it? Loses an H plus. So when HCO3- loses an H plus, what's left behind? CO3. But what's the charge now? Instead of -1, it's now -2. It's lost another plus charge, so it's now -2. And what happens to your water? H3O plus. Okay. Always make that. You always end up with that product right there. The conjugate base of the acid and hydronium ion. So this is the reaction for which the equilibrium constant is called the Ka of HCO3-. Okay? How can we abbreviate this? You can leave out the water and you can just abbreviate this as H plus. So you can say HCO3- yields carbonate plus H plus. Okay? What's the expression for Ka for this? The equilibrium constant. Ka then is equal to what? The Ka of bicarbonate ion would be concentration of carbonate times concentration of H plus over products over reactants, right? Over concentration of HCO3-. That's it. Provided those numbers, the values are at equilibrium. Okay. Otherwise, it's called your reaction quotient, right? So, yeah. Which of the following is the expression for Ka of HCO3-? Okay. I just gave you the answer to that one. Is it A or B? Okay, very good. What's the conjugate base of HCO3 minus? The conjugate base is what you get if you behave like an acid, right? If you behave like an acid, you end up being the conjugate base. So that's what you get after you've lost your proton. Carbonate ion, very good. Now, a molecule that's capable of donating more than one proton is what you would call a polyprotic acid. If it's capable of just donating one proton, how would you call it? If it's not poly, it's monoprotic acid. So if you have these kinds of molecules, then you can have several, ionization can occur in several steps. So what you would call the Ka1 or the K1 or the Ka would be the KEQ for the transfer of the first proton to waters. Okay. Once you get the conjugate base, if that conjugate base can still transfer another proton, the Ka for that is also known as the Ka2 of the original acid. So Ka2 or K2 of H and X, and here is greater than 1, would be the KEQ for the transfer of the second proton. For example, H3PO4. Okay? If I were to transfer one proton from H3PO4 to water, gives you H3O plus plus. What's left behind if I remove a proton from H3PO4? H2PO4, and its charge is now going to be -1, right? So the KEQ for this reaction is called the Ka1 or the Ka of H3PO4. Now, if I were to go further, if I let my H2PO4 minus transfer another proton to another water molecule, that gives me H3O plus plus, what's left behind now? What's the conjugate base of H2PO4 minus? One less hydrogen, one less charge, right? So HPO4, instead of -1, -2. So this is the KEQ for this is Ka of H3PO4. The Ka for this is the Ka2 of H3PO4. Okay? In other words, what we're saying is the Ka2 or K2 of H3PO4 is the same thing as the Ka of H2PO4 -1. Okay? If you look at this, if you just look at this, you'll say, oh, that's the Ka of H2PO4 minus. This is the Ka of the proton donor. But this, you can imagine this is having come from H3PO4, so you can say that's the second step in the ionization of H3PO4. So that's the Ka2 or the K2 of H3PO4. All right? What would be the Ka3? That would be the third step, right? So for the third step, you're going to have HPO4 negative gives you H plus, and I'm just abbreviating this now, H plus plus PO4 -3. So this is the KEQ for this is the K3 of H3PO4. Okay? So those are the names for the equilibrium constants, Ka1, Ka2, Ka3 for a polyprotic acid. Okay. And hydrolysis of metal cations, we talked about this earlier. We said could lead to an acidic solution. Okay, so aluminum chloride is acidic. Why did we say it was acidic? Your cation aluminum actually bonds with forms covalent bonds with 6 water molecules. So this is what you actually have in water. Okay. So metal cations in general, except those in group 1A and 2A. What are those in 1A and 2A? Sodium, potassium, magnesium, calcium. Okay, group 1A and 2A. Except for these, metal cations will generally hydrolyze. Okay, hydrolysis means simply reacting with water to give you H+. Okay, so in this particular case, your metal cation, let's say in general, if you have a metal cation with a charge of N+, okay, it will bond with several water molecules to form something like this. Generally, the number of water molecules that bonds to it is twice the charge. So aluminum has a +3 charge, so you can have 6 water molecules attached to it. We call that the coordination number. Okay. Now, M plus N, the metal, the cation, in this case the aluminum, for example, when it forms that bond with a water molecule, okay, that bond is said to be a coordinate covalent bond. And think of a coordinate covalent bond as sharing of electrons where one of the two participants is like a freeloader. If you look at this one, the shared electron is being provided by the water. Okay, so it's still a covalent bond just like any other covalent bond, except that when we use the word coordinate, generally we think about where it came from. And we say that this bond resulted from a water molecule donating a pair of electrons to the aluminum. Okay, so in this sense, this is a more general definition for an acid and base. If in this particular case we say aluminum is a Lewis acid, in the Lewis definition of an acid, anytime you have coordinate covalent bonding, okay, the electron pair donor is called the base, and the electron pair acceptor is called the acid. So this Lewis acid right here is the electron pair acceptor. And this water, you call this your Lewis base. This is called your electron pair donor. Okay? So your electron pair acceptor is classified as an acid in the Lewis definition of acids and bases. Okay? This is also known as an electrophile. Okay, why electrophile? What does phile mean? Philadelphia, city of brotherly love. This is an electron lover. Okay. An audiophile is someone who likes music. Okay. And electron pair donor. Okay. Look at this electron pair. It's looking for something positive. It's looking for a nucleus. A nucleus is positive. This is also known as a nucleophile. Okay. So what actually happens, okay, is, remember we said before that in the case of aluminum, okay, once you form that complex ion AlH2O6, 3+, what actually happens is, the reason you end up with an acidic solution is why? One of these hydrogens, we said, is going to transfer over to a water molecule, right? So that gives you AlH2O5, and one of the waters has lost its hydrogen, so it's now OH, right? So the charge is now 2+ instead of 3+, and then the other H has now gone on to the water molecule. So this is the reaction. So in this reaction, what's the Bronsted acid? This whole ion right here is your Bronsted acid. In the definition of acids and bases, according to Bronsted-Lowry, your hexa-aquo-aluminum complex, that's what it's called, okay, hexa means 6, is a proton donor. So this is your acid. And what's your base? The water is the proton acceptor, so that's your base. Okay? And so you end up with aluminum with 5 H2Os attached to it and an OH attached to it with a charge of +2. The Ka for this, the KEQ for this reaction is called the Ka of this complex, and it's known to be around 10 to the negative fifth. So it's significant enough to cause your solution to become slightly acidic. Okay. In comparison, acidic acid, vinegar has a Ka of about 10 to the negative 1 times 10 to the negative 5, so it's very comparable to vinegar. Okay. Now you can abbreviate this in general, so we don't have to worry about exactly how many water molecules are attached to the cation. We can just abbreviate this. We can just say this is aluminum plus 3 plus water. In essence, what it's done is pulled a hydroxide away from one of the water molecules, right? So you can say that's ALOH 2 plus H plus. So this thing right here is the abbreviation for what we wrote earlier. Okay? So hydrolysis reactions for cations would be like that. So if I were to ask you, what would be the hydrolysis reaction for, let's say, chromium? How would you hydrolyze chromium ion? If it were to hydrolyze, what would you get? How would you explain why a solution of chromium ions might be acidic? You'd say it can pick up basically an OH from a water molecule. So that gives you chromium CrOH with a 2 plus charge. And what's freed from water? An H plus. That would be a hydrolysis reaction. Okay? All right. So Ka of HSO4 minus is also known as the Ka2 of what? Is it A, H2SO4, B, H3SO4, or C, SO4 negative 2? Okay. This is the second step for, how quickly you forget. Let's do it. Let's go over this again. Ka2 of what? What's Ka of HSO4 minus? Ka means it's donating a proton to water, right? So I can abbreviate that using this. I can just say HSO4 minus gives you H plus sulfate. This is step 2. What was step 1? Step 1 forms this, right? HSO4 minus plus H plus coming from what? H2SO4. So it's the Ka2 or the K2 of H2SO4. So the Ka of HSO4 minus is the Ka2 or the K2 of H2SO4. So the answer is A. All right, let's try this one. For which of the following is the K equilibrium constant called the K2 or Ka2 of H2CO3? Is it A, B, C, D, or E? K2, that means second step, right? Let's take a look at this. You say this is what? That's K1, right? Or Ka1. That's the first step. K2 means after you've taken out one hydrogen, so this must be your reactant, right? But Ka or Ka2 means reacting with water, so it can't be this. It has to be reacting with water, transferring a proton to water. Okay? So which one is it, B or C? Let's see what you pick. C. Very good. Reset. Here you have H plus donating to water, gives you H plus, and then you get your carbonate. Okay? So that is the correct answer, C. Okay, this might be a good time to stop. We're going to go over base ionization next.